everyone, and welcome to this explainer. Have you ever actually stopped to think about how modern mass production or even global logistics really work behind the scenes? I mean, we totally take it for granted, right? We buy a product and all its little pieces just magically fit perfectly together. But creating that perfection? It's absolutely not magic. It is a rigorously structured science. So let's dive right into this incredible, kind of invisible hero of manufacturing that literally makes our modern world possible. Okay, just to put things into perspective, check out this massive number, 150 million. Now that's not a dollar amount, it's not a country's population. No, that is the total number of individual measurements required to make sure a single Boeing 747-400 aircraft is put together safely and correctly. It's wild. An aircraft like that has roughly 6 million individual parts. And get this, each one of those parts needs to have about 25 distinct features checked. If we didn't have an incredibly advanced system for measuring, organizing, and verifying all 150 million of those data points, well, that plane simply wouldn't fly. Section 1. The magic of interchangeability. This right here is the absolute bedrock of mass production. Think about a completely everyday scenario. Say you have an old lawnmower. You snap a bolt, and years later you head to the local hardware store to buy a replacement. You bring it home, pop it in, and it threads in flawlessly. That relatable, everyday magic relies 100% on our core concept for today, which is engineering metrology. Now, metrology is the science of measurement, but in the engineering world, we're dealing strictly with geometric measures. We're talking about things like length, diameter, out of roundness, angles, flatness, profile, the whole shebang. We're not testing how strong the metal is or what its chemical makeup is. That's a totally different department. Engineering metrology focuses purely on physical geometry, just to ensure parts fit together properly and function exactly as they're supposed to for their entire lifespan. All right, section 2, from analog to digital, where we'll look at the incredible evolution of the tools used to make these critical measurements. Consider the stark contrast between the old and the new here. On one hand, you've got a classic analog micrometer. Honestly, it's a beautifully crafted tool, but using it relies entirely on the physical skill and, quite frankly, the good eyesight of the person using it, who has to carefully read those tiny, tiny little graduated lines. But then, fast forward, and you have its modern cousin, the digital micrometer. Not only does this give you an instant, unmistakable readout, which totally eliminates human reading errors, by the way, but it can also be easily hooked right up to microprocessors. That's a huge deal, because it means measurement data can be fed in real time straight into a factory's statistical process control system. But listen, whether you're using analog or digital tools, there's this overarching insider heuristic in the industry known as the Rule of 10 or the gauge maker's rule. Basically, it states that your measuring instrument absolutely must be 10 times more accurate than the dimensional tolerance of the part you're actually trying to measure. So if you need a part to be accurate to 1/10 of a millimeter, your measuring tool has to be accurate to 1/100th of a millimeter. It makes perfect sense, right? You just can't verify precision unless your instrument goes way, way beyond the precision you're actually aiming for. Which brings us to section 3, modern measuring marvels. As we step inside today's state-of-the-art facilities, the scale of things changes dramatically. Seriously, just look at the sheer scale of this machine. This beast is a coordinate measuring machine, or CMM, and it's specifically designed to measure entire car bodies. It boasts a staggering measuring range, like 6 meters long by 1.6 meters wide by 2.4 meters high. But here is the crazy part. Despite being literally large enough to park a car inside, it operates with a sub-micron resolution of 0.1 micrometers. Just let that sink in. It's measuring the entire frame of a massive car down to a fraction of a single human hair. It's unbelievable. So how does it actually do that? Well, to maintain that kind of jaw-dropping accuracy over such a huge area, this machine uses something called active temperature compensation. It actively adjusts its own calculations based on the room temperature, specifically between 16 and 26 degrees Celsius. Because, as we know, metal naturally expands and contracts with heat. It also uses 2 simultaneously controlled heads equipped with touch trigger probes that can move fluidly in full 3D space. And obviously, a machine like this needs software-controlled collision prevention, because the very last thing you want is for these highly sensitive, ridiculously expensive probes to accidentally crash into the car body while they're zipping around at high speeds. Okay, but what if you literally can't touch the part you need to measure? Well, that is where laser micrometers come into play. Instead of using a physical probe, a laser beam quickly scans the workpiece. And I mean quickly, we're talking around 350 times a second.
Because there's zero physical contact happening, these things are absolutely perfect for parts that are, say, way too hot to touch, or parts flying down a continuous production line, or even flexible materials that would just squish or deform if a physical probe poked them. They rapidly scan the object and create what's known as a point cloud to verify the exact surface coordinates instantly.
All right, Section 4, automating the process. Let's see what actually happens when we integrate these incredible tools right into the production line itself. So, back in the day, manufacturing leaned heavily on post-process inspection. Basically, you'd make a batch of parts, pull a few off the line, and measure them. But if they were wrong, well, yikes. You just manufactured a whole batch of very expensive scrap metal. Today, though, we've shifted towards in-process, or real-time inspection. By slapping those laser scanners and digital sensors directly under the production line, we can monitor dimensions continuously, right as the parts are being made. The system is so smart, it can actually detect if a part is just starting to drift out of spec, and it feeds that data right back to the machine so it can correct itself before a single bad part is ever even produced. It's a total game changer. Now, you might be wondering, hey, if a machine is set up perfectly to begin with, why would it suddenly start making a slightly different part? Well, the technical realities of the factory floor are surprisingly volatile. Variations can pop up just from slight inconsistencies in the incoming raw materials. Or consider thermal distortion. As the machine runs all day, it gets hot and its own metal parts actually expand. Plus, cutting tools, dies, and molds, they physically wear down bit by tiny bit with every single part they pump out. And of course, there's always good old human error. This kind of random, everyday variation is exactly why continuous automated monitoring isn't just nice to have, it is absolutely crucial. Which brings us to our final section. Section 5. The truth about tolerances and controlling those tiny dimensions. Here is a hard, inescapable physical reality of our universe. Manufacturing two parts with precisely, absolutely identical dimensions is virtually impossible. I mean, there's always going to be some microscopic variation. Because of this, engineers use what we call dimensional tolerance. Basically, this is the permissible or acceptable window of variation in a specific dimension. As long as the part falls within that specific window, it's considered perfectly acceptable and will do its job exactly as intended. So the really crucial point here is how tweaking those tolerance limits completely changes the physical relationship between two parts. For example, if we design the tolerances to have a clearance fit, that means there's a tiny, deliberate bit of space left between the parts. That's what allows something like a wheel to spin freely on an axle. But if we overlap the tolerances to create an interference fit, the parts technically overlap on paper. This creates negative clearance, so you actually need massive pressure. We're talking hydraulic press levels of force to literally jam them together. And that creates a super tight, virtually permanent assembly without needing a single screw or drop of glue. And honestly, the crazy thing is just how fast this whole field is advancing. Industry surveys have revealed an astonishing trend. Dimensional tolerances on state-of-the-art parts are shrinking by a factor of 3 every single decade. Yes, you heard that right. Every 10 years, the tolerances get 3 times tighter. What was considered a ridiculously tight, high-tech tolerance 10 years ago, that's just standard today. We are literally pushing the extreme limits of physics and metrology to go smaller and smaller. But that actually brings us to a final, really interesting question. Is a tighter tolerance always better? It seems like it should be, right? But the answer, highly counterintuitively, is a resounding no. Designing unnecessarily tight tolerances doesn't make a product functionally better if it doesn't actually need to be that precise. Honestly, all it does is completely skyrocket your production costs. You just end up paying top dollar for advanced machinery, constant tool changes, and highly controlled environments for zero functional gain. The true art of engineering isn't about achieving absolute mathematical perfection. It's about finding that exact perfect tolerance that guarantees flawless performance while keeping the actual economics of manufacturing viable. So the next time you hold a perfectly crafted product in your hands, ask yourself this: are you holding a masterpiece of perfection or a masterpiece of acceptable imperfection?